So 4.1, we're going to be looking at the study of a different type of function. We just came up with the study of what type of functions? Polynomials. Yeah, and polynomials can be used to represent all kinds of wonderful real-world phenomena. And they're pretty easy to work with. They were the first types of functions that mathematicians tried to solve. They're smooth and continuous everywhere. Very easy to work with. But now we're going to be dealing with exponential functions, and I know you've had some experience with those. And a modified exponential function called logistic. Yeah, it's the just sound. So it's not; these aren't log functions; these are logistic functions. So where have y'all studied exponential functions before, or how did they come up in the past? What? Algebra? Oh, in Algebra 2, in another math class. Yeah, that makes sense. So you've seen these before. So maybe we should skip this section. What do you remember about an exponential function there, Zane? They have exponents, but polynomials have exponents too, don't they? Yeah, they sure do. Like x squared, x cubed. There's two types, exponential growth and decay. Yeah, just like x cubed could be increasing, and negative x cubed could be decreasing. We have functions that get bigger and smaller. What's that? There's always an asymptote. Watch your language. What type of asymptote? At least there's an asymptote. At least there's an asymptote. Yeah, so that's what you remember about them. Good, good, good. How about in science class? Exponential functions have come up, I'm sure, right? Biology? No? No, never? If you've gotten this far in a science class and the exponential functions haven't arisen? Physics? What about biology? No. Earth science? No. Wow. Okay. How about chemistry? No? Not yet. Have y'all heard about Fukushima, Japan? What happened in Fukushima a couple years ago? An earthquake? Maybe. That happened in New Zealand. There was one in the ocean. They just got hit with a tidal wave. No, how about 3 Mile Island? All right, Chernobyl. Yeah, nuclear fallout. Those were all 3 nuclear fallouts, and that deals with exponential, as you mentioned, decay and radioactive elements. Radioactivity. I know what that is, right? What is radioactive, Keithling? It's an energy, yeah, given off by an atom. Yeah, that can negatively affect your body for sure, right? Some of the elements in the world are stable. Like, what's a stable element? Yeah, thank you. The noble gases are not only stable, they are noble. Tyler, move your vehicle ASAP. Where'd you park? Tyler? Come on, Tyler. Yeah, they're noble. They're also stable. Carbon is very, very stable. There are some elements, though, that have no stable state. They only have a most stable state. Is all of carbon stable? Carbon-12 is stable, right? Every living thing has carbon-12. But what happens when the sunlight affects carbon-12? What's that? It sure does. It becomes unstable carbon-14, and every living creature has carbon-14 in them as well. And carbon-14 is what we call an unstable isotope. And so y'all heard carbon-14 before, right? You've never heard of carbon-14. How about like any anthropologists in here or paleontologists? No? Forensic dating. Dating, yeah. Like, y'all heard of carbon-14 dating, right? Please tell me yes. When you find an old shard at a dig site or something and you want to know approximately how old it is, they do what's called carbon-14 dating. How does that work? Why does that work? Because Exactly, exactly. Once something continues to exist, the carbon-12 remains the same because it's stable, but the carbon-14 begins to lose, and they have a very predictable, what they call half-life. A half-life. And what does a half-life mean? Every so many years, it loses exactly half of its mass. Yeah, half of its mass. And it happens predictably. So what they do is that for anything that they find, they can compare the carbon-12 against the carbon-14 that's in there, and they can approximate how old it is based upon the half-life of carbon-14, which is about 5,700 years. And so the half-life is an idea of exponential decay, okay, an idea of exponential decay. Now, what about exponential growth? Y'all have heard things in the real, like on TV, right? Man, that thing was going fast. It was like growing exponentially. Do all things that grow fast grow exponentially? No. But the proletariat used the word exponential growth to describe things that just randomly grow fast. And they never really sit down and do any kind of quantitative analysis to determine if it truly is exponential growth. How would you determine if something grows exponentially versus something that grows according to like a polynomial function like x to the fifth? X to the fifth grows pretty fast, doesn't it? Man, that thing was growing like x to the fifth. You never hear people say that. They either say gangbusters, it was growing like gangbusters, or it was growing exponentially. What about x to the seventh, x to the 100th power? Those all grow fast. So why is exponential always what people use when they want to describe things that grow rapidly? Yeah, in the long run, very good. In the long run, anything that truly grows exponentially will outgrow anything that grows according to a polynomial function. And it's simply for what you said. In a polynomial, the variable is what? The base or the exponent? In a polynomial, the base. And it has a whole number exponent. But in an exponential function, they flip-a-roo, right? You have a numeric base, and you have a variable exponent. And that's one of the ways you can kind of spot an exponential function. And so when the exponent is the variable, in the long run, it'll grow a lot faster, okay? But it does take some time. So I think that's why people just use the term exponential for things that grow very rapidly, even though not everything that grows rapidly is exponential. Okay, cool. So what are some things then that y'all know for a fact grow exponentially? In statistics, have you gotten to trying to determine if a set of data is polynomial or exponential yet? One of the main things about polynomial functions is that they can grow right out of the origin, right? Think about x squared. X squared comes right out of the point 0, 0 and starts increasing, right? So does x cubed. Exponential functions cannot grow out of nothing. Exponential functions always have to have a seeding value. They have to have an actual starting value. If there is no starting value, they don't grow at all. Polynomials can grow out of nothing. So what are some of the things then that you know grow exponentially that have to have a seeding value or a starting value? Stocks in the stock markets, possibly. They can grow very rapidly, but it's hard to predict if stocks are going to go up or down, right? They're so volatile. They've been trying to capture their behavior with the mathematical formula for years and have never been able to do it. The Black-Scholes formula came the closest. So maybe not stocks in general, but what about money? What about money? What if you go to the bank and you put like, you show up to the bank and you're like, I'd like to deposit some money. And they're like, sure, how much do you have? And you go, $0. And they go, okay, well, how much sense do you have? I've got none cents. Okay, that's pretty obvious, sir. You have 0 cents. I also has no pennies. All right, sir. Okay, great. When can I come back and get my money? That's going to be a silly conversation, right? Because you go to the bank, you put in no money, come back a year later, you're going to try and cash out what you put in. How much are you going to have at the end of a year, 2 years, 3 years? Nothing. You know, and if you're working behind the window, you're just, you know, like, manager, okay. It doesn't work that way. Polynomials, remember, can grow out of nothing, but exponential can't. Now, what if you go in the bank and you put in a dollar bill? And they're like, oh, great. I can see why you want to keep this dollar safe. Well, we have a savings account, sir, and our savings account earned 3% interest annually. Okay. Put your dollar in, come back a year later, without doing anything, you're going to have how much money? You're going to have an extra 3 cents. You're going to have $1.03. You earn 3 cents just for doing nothing, just for being willing to part with that dollar for a whole year, right? Okay, so exponential has to have a seeding value. Now, did that money grow exponentially? It went from $1 to $1.03. Most people say, "Wow, that's fast." It was growing exponentially. I don't know. How about this? What if you were in line behind the guy that put in $1, and you were behind him, and you put in $10, and you earned the same 3% interest, and you came back a year later? Now, how much money are you going to have? You're going to have 30 cents extra. And the guy that only had the 3 cents is going to be looking at you like, you got 30 cents and I only got 3? Man, you's lucky. You lucky. You get more money. We both had to wait the same amount of time, and you get 27 more cents than I do. Of course, he couldn't figure that out on his own. They had to tell him that, right? That's not fair. Is that fair? Is that fair? He put in more to begin with. Well, where did he get that extra money? That's what we want to know. We want that extra money too. Okay, so there's a guy behind the guy with the $10, and he's got $100, and he's putting in $100, and he comes back 1 year later, and he's getting what? I almost spit my coffee on you. You said $3. One guy's waiting a year, and he's getting 3 cents. Another guy's waiting a full year, same amount of time, he's getting 30 cents. And all of a sudden, some big high roller comes in there, does nothing for a year, and gets $3 extra? Why, that just ain't fair, is it? All right, what if a guy behind him comes in and deposits $100,000? When he comes back, he's going to have what? What's 3% of 100? 3. He's going to have $3,000. Wow. $3,000 for doing absolutely what? Nothing. Is their money growing exponentially? It is a set standard in growth, as you said. Yeah. One of the things that really sets exponentials off is the way they grow. The way they grow. So what is interesting about those 3 guys with their money besides their intelligence levels maybe, or their expectations? The guy who earned the more money or the most money was the guy who had more to begin with, right? Which is the American dream, right? The rich get richer. It takes money to make money. Well, without getting into that, the more you have, the more you earn, right? And the less you have, the less you earn. That right there is a quality of exponential growth. Similarly with decay, the more you have, the more you lose. The less you have, the less you lose. That is exponential growth. That is exponential decay. In other words, the growth occurs at a rate that is directly proportional to the amount itself. Does that make sense? It grows or decays at a rate that is directly proportional to the amount itself. That is not true with polynomial growth. That is only true with exponential growth. Okay, so apparently money then can grow exponentially. Now, they both earn 3%. So as you said, it was a constant standard of growth. Anything that increases or decreases by a constant percentage is another way to determine if something grows exponentially. So money grows exponentially, believe it or not. Money that earns a specific interest rate over time grows exponentially. What are some other things then, now that you kind of know the qualifications? The more you have, the more you get. The less you have, the less you get, which is why we need the seeding value. Or the things that increase and decrease by a constant percentage? What are some other things now that you can think of that either grow or decay exponentially? Food production. Well, it would be the more food you have, the more food you get. Is that true? Or the more food you produce, the more food you're going to produce in the future? Well, in what sense? In what sense?
Well, okay, I was saying like an orchard, you have 3 trees that produce fruit versus 30 trees that produce fruit.
Oh, so you're talking about population of trees.
Yes.
Yeah, populations in general, whether you're talking about tree populations, people populations, or bacteria populations, right? The more you have out there making more, right? So the more you have, the more you're going to get. The population of planet Earth has now reached 7 billion. Yeah. And so the population is increasing at a rate that is directly proportional to the number of people on the planet. The more people you have out there, the more people you have out there reproducing, the faster the population is going to grow. So populations grow exponentially. It works well with bacteria too. The more bacteria you have, the more bacteria you're going to get. Populations are another thing that grow exponentially. Good. What else? Math is cool. Pass it on. So-and-so voted for Trump. Pass it on. What happens around here on high school campuses, especially? Hey, Tyler parked in the teacher's spot. He thinks he's a teacher. Gossip. Rumors. Do they spread exponentially? The more people you have telling the rumor, the faster it's going to spread? Yeah. What? It's not quadratic. There's no way it's quadratic. Because quadratic can grow out of nothing. All right. Tyler, I want you to spread this rumor, okay? Come here. All right. Tell him. Same thing I told you. What did he tell you? Did he say anything? No. Is that quadratic? It might be. Quadratics can grow out of nothing. But can exponential? No, there's no rumor to spread if I don't tell you anything. So it can't grow. It can't grow. Right? If you don't have an original person at some point, I guess you would need 2 humans, right? We can't asexually reproduce. Then you're never going to have more people. If you don't have an initial population, you're not going to have populations after that. So exponential can't grow out of nothing. All right, so what do we have so far? Money grows exponentially because it increases by a certain percentage. Populations. Okay, now the reason I said biology is because y'all have learned cell division. What's that process called? Mitosis, right? What's halitosis? That's bad breath. Is that it? Could that be exponential? You can lose friends exponentially, right? Yeah. Mitosis or meiosis, whichever one you're talking about. What happens? One cell divides and becomes 2. Then 2 divides and becomes 4. And then the next generation would have how many? Whoa. 2, 4, 6, 8. That's a different thing. 2, 4, 8, 16, 32, 64, 128, 256. What's happening every generation of splitting to the population? It's not squaring. It's multiplying by 2. It doubles, right? It doubles. Is that exponential? Yeah, because the more cells you have out there that can split, the more you're going to have, the faster it grows. So it does grow at a rate proportional to itself. So if something doubles Is that the same as increasing by a certain percentage each generation? Yes. So let's think about it. Think hard. If something doubles, it increases by what percentage? Very good. 100%. If something increases by 100%, it doubles. If something doubles, it increases by 100%. So if anything that increases at a constant percentage rate or decreases is exponential, then by the same token, anything that increases by a constant factor times 3 every time, times 3 every time, or a third, or half-lives, right? A half, then it's going to be exponential. All right? So that's what makes something exponential. All right, let's go ahead then and intuitively define exponential growth or decay. A quantity could be anything, right? Could be money, could be rumors, could be bacteria. A quantity that increases or decreases exponentially will grow or decay, respectively, at a rate that is proportional to the current amount. That's a hugely important qualitative description of exponential growth or decay. The more you have, the more you get, or the less you have, the less you lose. All right, so we've already done example 1. Here's the formal definition of exponential growth or decay. We can model this now. A function then is said to be an exponential function of the form f of x equals a times b to the x power, where a is not 0. If a is 0, it wipes everything out and you get the x-axis. And b is either greater than 1, in which case you're going to have exponential, what we call growth, or the base is going to be between 0 and 1, in which case you're going to have decay. Now notice that the base cannot equal 1. What happens if the base is 1? What's 1 to any power? 1 to the second, 1 to the third, 1 to the fourth? It's just 1. It's a horizontal line. And of course, b cannot be negative either. B has to be either greater than 1, things are doubling every time, getting bigger, or between 0 and 1, they're halving each time, they're getting smaller. We call that exponential decay. Now, a is the number that's being multiplied by the base. That is what? It can't be 0. It could be positive or negative. It could be anything. This is called your initial value. And I write it down there, but I'll label it here. Now, in this case, initial corresponds to what value of x? What is the y-intercept here? How do you evaluate that? What's f of 0? Well, it's going to be a times some number to the 0 power. What's a number raised to the 0 power? 1. Good. So you get a times 1, which of course is a. So what important point is that on the graph? 0, 1, which is the y-intercept. Yeah. So your initial value is also the y-intercept of the graph. And the b itself is called the base. That's a good letter to use for something that's called the base. The base could be, it says any real number, but we already put restrictions on it over here. So it could be any real number greater than 1 or any number between 0 and 1. I don't want you to think that it can be negative. It doesn't have to be a nice number. It could be like 2.5. So it could be any real number as long as it's greater than 1 or between 0 and 1. Okay, here's some examples then of some exponential functions. This is what they look like. F of x equals 3 to the power of x. Now, why is that exponential and not polynomial? Yes, you have a variable in the exponent, and the base is 3. So this would be something that triples every value of x. It goes from 3, and then to 9, and to 27, 81, so on and so forth. H of x is equal to, is that 2.10 or 2 times 10? 2 times 10. So 2 would be your initial value, and the base would be 10. So this is something that increases by a factor of 10 each integer value of x. That's going to get pretty big pretty fast, but it starts with 2. Now, can you combine that and call it 20 to the x? Yeah, we went over that in the beginning of the year. You cannot multiply those. Those are not like factors. So you cannot do that. Just keep that in mind. You're going to maybe have an urge to want to do that later on. What would be the a value here? It's implied to be 1, right? And that would be the y-intercept. Good. Here's another one. 4 times the quantity 1/2 to the x. What's the base? 1/2. So this would be exponential decay because it's decreasing from left to right. And the y-intercept is what? 4. Good. All right, so let's go ahead and do what we did for polynomials. We're going to determine if each one is exponential e or not exponential n. Letter A. So e for exponential. The base is 7, and the exponent is x. Good. How about this one? X to the 7th. No, that one is polynomial. Now, which one is bigger for small values of x? X to the 7th is probably going to be bigger for relatively small values of x. But once you get outside of x equals 1, the 7 to the x is going to overtake it, and they won't cross anymore. So that's why we say in the long run, exponential functions go faster. All right, how about this one, x to the x? It has the variable in the exponent like we need for exponential, but it also has the variable in the base like we need for some kind of power function or polynomial. So it's kind of a hybrid, huh? H for hybrid? We'll put that n for not an exponential. This one is called an Aleph function. And you don't really need to know that, but Aleph being the first letter in the Hebrew alphabet, this is a function that actually grows faster than exponential. But it's not purely exponential because it does not have a numeric base. All right, how about this one? -2 times 15 to the x plus first power. It is exponential. This would be a transformation of an exponential. As long as you have a variable in the exponent and a numeric base of 15, it's good. That's exponential. 4 pi to the x. What's the variable? X. It's in the exponent, so that's good. What's the base? Just pi. Good. Just pi. And is that a legal exponent? Or is that a legal base? Sure. Yeah, as long as it's a real number between 0 and 1 or greater than 1. Would that be growth or decay? It would be growth, yeah. Would it be growth or would it be ooh growth? Just growth, right? It's not ooh growth. You know what's ooh growth? Exponential decay. Ooh, growth. Even though it's decay. All right, how about this one? Growth or decay? It's got a variable exponent, and it's got a numeric base. It's looking like it's exponential. Yeah, it's 1. What's another name for this function? 3. The horizontal line, y equals 3. It's not exponential at all. How fast does that grow? It doesn't, right? I'm just a 3. Yeah, I'm always a 3. And I'm sitting here on capital. That doesn't work. Never mind. -3 to the x. Exponential, yes or no? They're getting trickier. It has the variable exponent. That's good. What's the base? -3 or 3?
It'll be 3 times maybe 1.
Let's talk to your dear Aunt Sally. Please excuse my dear Aunt Sally. Parentheses, we have none. Exponentiation, it's 3 to the x. And then multiply, it's -1. So that is how you can write it. Does that work? Yes, it's exponential. Yeah, you're right. It's -1 times 3 to the x. So that one is exponential. Whereas this one over here, now with the parentheses there, the base is -3. Is that a legal base? No. So this is not exponential. The reason that's not going to work is when you raise -3 to real number powers, when you raise it to integer powers, it's going to oscillate like -3 or 1, -3, 9, -27. It's going to oscillate back and forth. But when you raise it to like real number powers, you'll break your calculator. It just jumps back and forth. It's not smooth at all. So don't do it unless you're in a safe place and you've got your safety goggles on. Your calculator will break. All right, so that's no. How about this one, 0 to the x power? No. No. Again, the base can't be 0. What's another name for this function? Zero to the first is 0. Yeah. What about 0 to the 0 power? This one's tricky. This one is the graph of the x-axis, except at the origin there's an open circle. 0 to the 0 is undefined. Okay, it's indeterminate. But 0 to the first is 0. What about 0 to the negative first? Let's talk about that. Maybe I rushed ahead on the. What's another name for 0 to the negative first? 1 over 0. So we can't even have negative exponents. Oops. So it's only going to be that. We don't even need to do that then. That's another name for the function. All right. So that one's not. Doesn't work, except for positive values of x. How about this one? Now, remember when we had polynomials, we had to be careful, because if they cleaned up to be a polynomial, they still could not be a polynomial, because we have to look at the domain of the original function. And in this case, we could write that as 3 times 4 to the power of x, yeah? And that would look like an exponential function. But we haven't really talked about the domain yet. So only if the domain of the original and the one we simplified it to be are the same will this in fact be exponential. So let's come up here and just analyze this. We're going to be going off to the side here and looking at the domain. If I look at y equals 2 to the x for hypothetical representative exponential growth function, like mitosis, cell division, doubles every integer power of x, what do you think the domain of that's going to be? Let's go ahead and plot some points, like we did in Algebra 2 or Algebra 1 when we were trying to figure out what a graph looks like. Oops, I don't know why I did that. Let's go, when x is 0, what do we get? 1, right? When x is 1, we get 2. When x is 2, we get 4, right? When x is 3, we get 8. So you can see that this is going up very, very rapidly as we go to the right. What about over here? What about to the negative first? What's 2 to the negative first also known as? 1/2. Ooh, that's down here. At negative 2, what's 2 to the negative second? 1/4. Yeah, at negative 3, what's 2 to the negative third? 1/8. It's going like this. It's getting smaller and smaller. Will that thing ever equal 0? No. It's going to get smaller and smaller as you go out to the left, but it'll never equal 0. Even if you have like 2 to the negative millionth power. That's going to be 1 over 2 to the positive millionth, which is super duper small. But it'll never equal 0. It'll just approach 0. So that's why, Tyler, we have a what on the x-axis that affects the left-hand behavior of the graph? A horizontal asymptote. Good. But it only affects the growth function on the left-hand side. What would the domain of that function be? Is there any value of x that we are not allowed to plug in? Well, 2 to the 0 would be the y-intercept. Remember, we're trying to avoid division by 0, square roots of negatives. And even if I plugged in a 1/2, right? 2 to the 1/2 would be the square root of 2. So I will be taking square roots, but it's always of 2. So are there any restrictions to the domain of an exponential function? Nope. The domain of any and all exponential functions is going to be just like polynomials. They're defined for all real numbers. Now notice the range is going to be different. The range in this case is bounded below by 0. The range is everything strictly greater than 0. But the domain is all real numbers. And that's true for every exponential growth or decay function. That's really cool. So we know that this is going to be an exponential function if the original one has a domain of all real numbers. Now we can either write it as 3 times 4 to the x, or we can write it as 3 times 1/4 to the negative x, because 1 to the negative x is still 1. That would be a transformation of a exponential decay function. because 1/4 is less than 1. What does multiplying any functions in the equation, the x by a negative, do to the graph? Do you all remember? Flip it across the what? No, that would be if it's in the front. That's an x-axis reflection. Here your x's are now changing, so a positive and negative x interchange. It would be a y-axis reflection. So if you take a decay function that falls from left to right and you reflect it across the y-axis, now it's going to become a what? A growth function. And so these are actually equivalent. So is it, in fact, an exponential function? Yes. Yes, it is. And it turns out to be exponential growth. So yes, 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 it is. All right, let's go ahead and evaluate. It says calculator. I don't think we need to. What is f of 2? Well, it's 1/3 to the second power, which is what? 1/9. Okay, so come out right here to 2. 1/9 is right there. What about f to the negative 3/4? That's going to be 1/3 to the negative 3/4 power. If we wanted to evaluate that, we could flip it and say it's 3 to the positive 3/4 power. What's that going to be? Is that going to be a nice number, the 4 through to 27? No, I don't think so. Let's just think about what this function looks like. What's happening as you increase x by positive integers? X to the 0 is 1, right? We know that. And then when you go to x equals 1, it's 1/3 of what it was before. Then it's 1/3 of what it was before. Yeah, so this is going to be exponential decay. So for negative values, it's going to look like that. It's actually going to increase. So here's what an exponential decay function looks like. It falls from left to right. It's decreasing from left to right. Now the horizontal asymptote affects the graph on the right-hand side, which is exactly why carbon-14 dating works. Because when the organism dies here at t equals 0, the carbon-14 begins to deteriorate at a consistent rate. It loses half of its mass every 5,700 years. And what does the model then say over time? Will that organism ever run out of carbon-14? No. So as long as we have the materials in hand and we have the devices that are able to extract it and measure it, we could then compare it to its stable carbon-12 and figure out how old it is based on the half-life of carbon-14. There will always be a trace amount left. It'll never equal 0. All right, sweet. So very quickly here, this example 4, and I'm going through kind of quickly here, is just to show you the difference between a growth and decay function. So let's go ahead and look at y equals 2 to the x in blue. And we kind of already know what it looks like. It looks something like that. So you can draw it first. What's the y-intercept? 0, 1, right? And then the y values for positive values of x will go 2, 4, 8, 16, so on and so forth. And as you go to the left, they'll go 1/2, 1/4, 1/8, 1/16. What I want to do is I want to draw now, let's use a contrasting color like green. I want to sketch the graph of y equals 1/2 to the x. Now that's going to be decay. Yes? Let's go ahead and look at our algebraic transformations here. 1/2 to the x is the same as 2 to the negative 1st to the x power. Would you agree? And now what can we do with our exponents? So when you raise the power to a power, you multiply, so that becomes 2 to the negative x. And so what that allows us to do then is to create the graph of 1/2 to the x by modifying the graph of 2 to the x. Nolan, how would we generate the graph of 2 to the negative x from 2 to the positive x? What does multiplying x by a negative do to any graph? The y-axis. Good. Yeah, we just mentioned that. So if you were to reflect that across the y-axis, it would decay now at the same rate it was growing on the other side there, or decaying on the other side. So those would be mirror images of each other across the y-axis, and you get y to the 1/2 x. Okay, and similarly, y to the 3x would be the mirror image of y to the 1/3 x, right? And what about y to the 1.5x? It would be the mirror image of what decay function? 2/3. Very good, because 1.5 is 3 halves, and you flip it and get 2/3. So the growth and decay are going to have mirror images of each other. One of them is going to grow at about the same rate. The other one's going to decay. And it works with all of them. Now, let's go ahead and choose a different set of flavors here that contrast. I'm going to use red. Let's go ahead and graph e to the x. This is going to be essentially your parent function, not 2 to the x. What is e approximately? 2.718. So what is e to the 0 power? Still 1, yeah? But as I go up to the right, where is the graph of e to the x going to be in relation to 2 to the x? Above or below? If you multiply something by, you double it every time versus almost triple it, 2.718, the one that's almost tripled is going to grow faster, right? And so the y value should be bigger. So you can compare exponential functions that grow compared to each other. Essentially, for huge values of positive x, or any positive x values for that matter, the bigger the base, the wider the graph. Steeper or less steep? Steeper. Yeah, that makes sense. But what happens when you go the other way? It gets bigger faster for positive values of x, but it'll get smaller faster for negative values of x. So they intersect there. And now you can reflect it across the y-axis and get the graph of 1 over e to the x, which is the same as e to the negative x. Because it's going to be steeper, it's going to look like that, and it's going to look like that. And that'll be the graph of 1 over e to the x. So we can go ahead and make this statement right here. For growth, comma, the bigger the base, the wider the graph, did we say? The steeper the graph. And you could say that in both directions. It's going to go to infinity faster on the right side, and it's going to go to 0 faster on the left. But what can we say about the decay functions then? Is it the same thing? Well, let's see. Which number is bigger, 1/2 or 1 over e? 1 over e is bigger? 1 over e is smaller. 1 over e is smaller. And so in this case, for decay, the smaller the graph, the smaller the base, the wider the graph. Steeper. Yeah, or you could say the smaller the base, the steeper the graph. Whatever you want to say. So for decay, it's the other way around. The smaller the base, the steeper the graph. Or if you want to flip it around, you can say the bigger the base, the less steep the graph. It doesn't really matter. They do have an a value. I was going to mention that. What do they all have in common besides being exponential? Well, they all have a horizontal asymptote that only affects one end of the behavior. They all go to infinity on the other side. But they all pass through what common point? Yeah, they all have a y-intercept of 1. And so the implied a value on each of them is 1. 1 times 2, 1 times e. Yeah, cool. And there is a summary, then, of what we just kind of did for other values. Now, this one doesn't have e drawn in there, but e would fall between 2 and 3 right there. And 1 over e would fall between 1/2 and 1/3. All right, so now you know what makes an exponential function exponential. You can identify it from the equation, you can identify it from the graph, and you can identify it from a qualitative description. So real quickly, who would like to summarize the qualitative behavior of an exponential function? An exponential function will either grow or decay at a rate that is directly proportional to? What's that? The quantity itself, its current amount. So the more you have, the more you get. The less you have, the less you get. The more you have, the more you lose. The less you have, the less you lose, right? And they have to grow out of something. They cannot grow out of nothing. They have to have a y-intercept that's not 0. They have to have a seeding value. I got $0. I come back in a year, I got $0 still. That's not exponential. Okay? That's just dumb. Yeah. All right. Be starting on the homework assignment. Go ahead and walk to the door. You got about 10 seconds so that you can get to your next period, your favorite class, I'm guessing, Coleman.